On the keys, if you please, it's Ryan.
It's time for Maths with Mr. Thomas.
Chapter 7, lesson number 2, proof by induction 2, harder examples. So in the last lesson we were introduced to what proof by induction is, and we went over 6 standard examples. Make sure you're okay with them before moving on to these. So there are 4 examples here. Feel free to skip to whichever one you like. So when working through proof by induction, a very quick recap. What is that word that I like to use? SACC. Perfect. If you think about the word SACC, S-A-C-C, it helps you remember the order that you need to work through these questions. Just remember, S is your starting value. You always want to prove that the statement is true for a starting value. A lot of the time that will be n equals 1. A is for assume. You want to assume that it's true for n equals k, and if it is, you want to then consider n equals k plus 1 and try and prove that. You then want to write your conclusion, which will follow all the steps that you just did. So let's jump in to example 7. Remember, examples 1 to 6 are in the previous lesson. So for this one, prove by induction that 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 plus all the way up to 1 over n times n plus 1 is equal to n over n plus 1 for all n belonging to n. So in other words, n is going to be your natural number. So the first thing we need to do for this, you will see that in the last lesson, well, we had something equals something, and it wasn't anything as complicated as a series when it's written out like this. So what we need to do is we need to write this out using sigma notation. So to do that, what we need to think is, right, well, what does that actually mean? How do we get to that? Well, if you write it out using sigma notation, you will see that what you have is, well, you've always got 1 on the top. So we're keeping with 1. Then what we're doing is, well, we're going to be starting with, at the bottom, we've got 1 in the first. Then in the second, we've got 2. Then we've got a 3 and so on. So really what we're doing is we're starting with this value here. Let's just call that r. So let's say r equals 1. That is what we'd start with. What we're doing is we're multiplying that by the number above it. So when r is 1, we do 1 times 2. When r is going to be 2, we do 2 times 3. When r is 3, we do 3 times 4. So we're taking whatever r is and we're multiplying it by r plus 1. And where do we go up to? Well, you can see that we're going up to the last number that we have. We've got 1, then 2, then 3, and the last one, well, it's not a number, it's n. So we're going all the way up to n. You could also get that from this bit here. You can see it is a very similar form. All we're doing is we're swapping the n's with r. So really what we want then, rather than proving all of this series equals n over n plus 1, really we're proving the sum of 1 over r times r plus 1 equals n over n plus 1, going from r equals 1 all the way up to n. So that is what we have to prove. Once it's written in that form, it is very similar to one of the examples that we did in the last lesson. So to work our way through this, again, think about the word SACC. S is for start. So you want to start off by considering a small value, a starting value. So let's say n equals 1. Take the left-hand side, so the sum of 1 over r bracket r plus 1, going from r equals 1 all the way up to 1. Remember, you're replacing n with 1. Well, that will equal. But what you do here is you sub in to this fraction 1. Replace r with 1 and you'll end up with 1 over 1 times 1 plus 1. In other words, 1 over 2. That's what you'll end up with. Looking at the right-hand side, if you replace n with 1, you will have 1 over 1 plus 1, which is also 1/2. So you can see that the left-hand side equals the right-hand side. Don't finish off by saying that. You want to take it a bit further. If the left-hand side equals the right-hand side, what does that actually mean, Amy? Perfect. It means that the statement is true for n equals 1. So write that down. So we have taken our starting value. We now want to assume that it's true for n equals k. Write these bits down just word for word. So assume true for n equals k. If it is, then what you have is the sum of 1 over r bracket r plus 1, going from r equals 1 all the way up to, well, instead of n, you've got k. And that would equal, well, instead of n over n plus 1, you would have k over k plus 1. So all you do is you're rewriting your statement, just rewrite this, but replace n with k. That's all you do for that step, so we have assumed that it's true. What we then do is move on to consider, and what do we consider? N equals k plus 1! Perfect, so you consider n equals k plus 1. So, if you think 1 over r bracket r plus 1, you want the sum of that going from r equals 1 all the way up to k plus 1. What will that be equal to? Well, hopefully you know from the previous lesson, there were 6 examples there. You should know already that to get the sum going from r equals 1 all the way up to k plus 1, really you could miss out that last term, miss out the k plus 1 and take the one before that, which will be k. So that will be the sum of 1 over r bracket r plus 1 going from r equals 1 all the way up to k. However, if you do that, that's going to be when you sub in 1 in place of r, then 2, then 3, then 4, all the way up to k. But we're wanting to go all the way up to k plus 1. And really what we've done is we've missed out that last term. We've missed out the k plus 1. So now what we need to do is we now need to sub k plus 1 in place of r. And that will be the last term that we would have to add on. So we would add, and then you'd have 1 over k plus 1 times, and that'll be k plus 1 plus 1. So all you do is sub k plus 1 into whatever you have here. That's what you'll add on. Let's go over the page. Above the pink line is just what we had in the last slide. Taking it further from there, well, you can see that you've got the sum of 1 over r bracket r plus 1 going from r equals 1 up to k. But you know from this line what that is equal to. The sum of 1 over r plus 1 going from 1 to k is equal to k over k plus 1. So all you do is you swap that in here. So we can say that is going to be k over k plus 1, because that's what you swap that with, plus, and then we keep this just as it is. Although, you know, 1 add 1 is 2, so you could write that down. Where do we go from there? Well, look at our answer. You can see the answer that we want to get down to is n over n plus 1. It's a single fraction. So what we need to do now is add the fractions together. Marta, how would you do that? Add them. Perfect. So just add the fractions. And how would you add the fractions? What do you need? Lowest common denominator. Perfect, you need the lowest common denominator. So you can see this fraction is over k plus 1. This one is over k plus 1 times k plus 2. This fraction here, you also need to bring in a k plus 2. So multiply the top and the bottom by k plus 2. So you'll have k times k plus 2 over k plus 1 times k plus 2 plus, and then just keep this one as it is. After that, you have the same denominator. Woo! So you can add the numerators. So you've got k bracket k plus 2 plus 1 over that denominator. From there, just multiply out the brackets. Make sure whatever you do not cancel out the k plus 2. That will not work because that's no longer k plus 2. You're multiplying it by k and then you're adding on 1, so you cannot just cancel. Multiply out the brackets, that will give you k squared plus 2k plus 1 over the k plus 1, k plus 2. And then from there, does anybody see what you do after that? Daniel? Brilliant. You would factorise. So if you factorise that top line, what does it give you, Daniel? Brilliant. You'd have k plus 1 times k plus 1. What's the whole point in doing that, Poppy? Brilliant. If you cancel the k plus 1 at the top and the bottom, it'll leave you with k plus 1 over k plus 2. Once again, look down to the answer that you want to find. This is what our question was. We want to get down to n over n plus 1, so we want it written in terms of n. But first of all, before you get that, write it in terms of k plus 1, because remember, you're considering n equals k plus 1. So k plus 1, well, we've got that at the top, but k plus 2 in terms of k plus 1, well, you know that is going to be k plus 1 plus 1. What you can do after that is you can replace the k plus 1 with n, because you considered n equals k plus 1. We are now down at n over n plus 1. That is what we wanted. That is what we had to prove. Woo! Well done. So we had a starting value that we then assumed it was true for n equals k. Then we considered n equals k plus 1. We've now got down to the answer that we want. Big smiley face. Yay! And now you need to write your conclusion. So the conclusion, you just go through all of these steps. So what did you do? Well, we looked at n equals 1, first of all. So you can say the statement is true for n equals 1, and assuming it's true for n equals k, it's also true for n equals k plus 1. We just proved that. So by induction, the statement is true for all n belonging to n, your natural numbers. Remember this very, very last part, you just get that from the question. The question said to prove it's true for all n belongs to n. So just take that from there. Well done. That's example 7. Example 8, prove by induction that 2 plus 5 plus 8 plus ... equals a half n bracket 3n plus 1 for all positive integers n. Anybody have any ideas how you would do this one? Perfect. You know when you are solving one of these proof by induction questions, you are wanting to use sigma. So you're wanting the sum of. And really this is the sum of terms in a sequence. We have our series here. What type of series is it? Philip. Perfect. You can see it's an arithmetic series. And it's an arithmetic series because you're adding on the same thing every time. So for an arithmetic series, or an arithmetic sequence, 2, 5, 8, and so on, you know that you can write down easily your first term. In this case, the first term is just a equals 2. And there's also a common difference of, it's a common difference of 3. So you have a first term a equals 2 and a common difference of 3. Really what we're wanting to do is we want to find a formula for these terms. In other words, a formula for the nth term. Because once you have a formula for the nth term, you can say it's going to be the sum of all of those terms, going from r equals 1 all the way up to something. So your first term, your second term, and so on all the way up to n. So what we need to do then is to find a formula for the nth term. And if you have an arithmetic sequence, such as this one, with 2, then 5, then 8, and so on, you know your formula is un equals, does anybody remember from the last chapter? Brilliant, it's a plus n minus 1d. So for this series, what we have is un equals, replace a with 2, and then replace d with 3. So we have 2 plus n minus 1 times 3. Multiply the brackets, you'd have 3 times n and then 3 times negative 1. So that is what you have there. And then after that, tidy it up. So you've got a 3n take away 1. So that is going to be the formula for really your general term of that series. However, what we want to do is we want to write that using sigma. So we can now say then that what we really have is the sum of, going from r equals 1 all the way up to n, we've got the sum of that series there, the 3n take away 1. However, we're going to replace n with r. So we have the sum of 3r take away 1 going from r equals 1 all the way up to n. So really what we've got then is we would just sub in 1, so do 3 times 1 take away 1. That would give you 2, well that is your first term. Then you would do the 3 times 2 take away 1, then 3 times 3 take away 1, and so on. And you're really going up to n. And that will be equal to the half n bracket 3n plus 1. That is what we're being asked to prove. So let's do that then. So if we're asked to prove the sum of 3r take away 1, going from r equals 1 all the way up to n, well, we want to get down to this. This is the answer that we want. And to do that, we have to go through this proof by induction. So, writing down SACC, S-A-C-C, starting value. So let n equal 1. If n was equal to 1, then our left-hand side then would be the sum of 3r take away 1, going from r equals 1 all the way up to 1. So in other words, we're just subbing in 1 in place of r. So 3r take away 1 would be 3 times 1 take away 1, which is equal to 2. So our left-hand side is 2. Our right-hand side, what is the right-hand side equal to? Well, if you replace n with 1, you'd have a half times 1 times 3 times 1 plus 1. And that would equal half of 4, which is 2. We can see then the left-hand side equals the right-hand side, woo! And that means then that the statement is true for n equals 1. So that is us, we have dealt with the starting value. We now want to assume that it's true for n equals k, so we write that down, and if it was true for n equals k, then the sum of 3r take away 1, going from r equals 1 all the way up to k, would equal, well, instead of a half n, you'd have a half k, and instead of 3n plus 1, you'd have 3k plus 1. So all you're really doing is you're rewriting this statement, but you replace every single n with k. So you're assuming that is true. After that, you want to consider. So you consider n equals k plus 1. So considering n equals k plus 1, you've still got the sum of 3r take away 1, but this time you're going from r equals 1 all the way up to k plus 1. Very similar to the last examples, you know the sum of 3r take away 1 going all the way up to k plus 1 is really just the sum of it going up to k. So you'd sub in 1, then 2, then 3, all the way up to k. But remember, you're wanting to go past that with k plus 1. So you'd also have to add on what you get when you sub k plus 1 in place of r. So if you sub that in, you'd have 3 times the k plus 1 take away 1. And that would be your last term. Going over the page, well, everything above this pink line, all of that was just on the last page, but where do we go from there? Well, we are wanting to replace this sum of 3r take away 1 going from r equals 1 all the way up to k. We can see there that it's equal to a half k 3k plus 1. We're assuming that is true. So we can sub that in there. So that will become then half k 3k plus 1 plus 3k plus 1 take away 1. Really, the rule is after that stage you factorise. Can you factorise here? Well, no, you can't. If you can't factorise, then it is best to start multiplying out brackets. So multiplying them out, that will give you a half, and then we're just keeping that as it is because we know we're wanting the half at the start, so we do eventually want to take that out. So just multiply by the k, so that will give us 3k squared plus k plus 3k plus 3 take away 1. Simplify that, so you've got 3 take away 1, so just write that as 2, and then from there have a think about what you want to do. Well, always have a look at the answer that you want. We want to get down to half n 3n plus 1. We have that half out as a common factor. That is what we need. Well, we've got half here, but we don't have a half here, and we don't have a half here. But what we could do is we could try and take that out by rewriting the 3k and rewriting the 2. If you imagine it just now, 3k is the same as 3k over 1 and 2 is the same as 2 over 1. In order to write it in terms of halves though, well, we need a 2 on the bottom of the fraction. So you multiply both the numerator and the denominator by 2. Do it for the 3k and that will give you 6k over 2. And if you do it for the 2, if you multiply both of them by 2, that will give you 4 over 2. The whole point in doing that is you can see here you've got a half. You can see here as well, you've got a half, and you can see here you have a half, which means then you can take them out as a common factor. So if you take out the halves as a common factor, you will have a half, and then put in big square brackets. I've still got this 3k squared plus k. I've still got that 6k, I'm just taking out that divide by 2. And I've still got this 4. Again, I'm still taking out that divide by 2, taking out the half. So that is where we are next. From there, where do we go? Well, you could have any other choice but to just tidy this up. Really, you don't need the brackets here. You're not really multiplying them by anything. It's just going to be 1 times. So you've got a 3k squared plus k plus 6k. Well, k plus 6k is going to be 7k, and you've also got that 4. After that, you want to factorise this bit in brackets. If you factorise that, just go off to the side and do that. Bump-a-dump-a-dump. And you will get k plus 1 times 3k plus 4. Again, going back to the answer that we want, this is what we want to get down to, a half n, 3n plus 1. So we're wanting it in terms of n. Before you get it in terms of n though, get it in terms of k plus 1. We've got a k plus 1 there, but here we don't. So to get k plus 1, well, to get the 3k, you're going to have to multiply k plus 1 by 3. So you're going to write that as 3 times k plus 1. If you do that, well, you've got a 3 times k, which is a 3k, that's what you want that bit. And then you've got a 3 times 1, which is 3, but we've got 4 here. So how do you correct that? Well, you also have to add on that 1. So we're rewriting 3k plus 4 as 3 times k plus 1. The 3 times k gave us 3k, 3 times 1 gave us 3, so we also need to add 1 more to make that 4. We've done that, and we've now got a k plus 1 and another k plus 1. So on our very, very last line, what we're doing is we're replacing that k plus 1 with n. So we have a half times n times the 3n plus 1. Have a look at the answer. You can see it is the exact same, minus those brackets. But that is what you wanted to get down to. After that, we considered n equals k plus 1. We did prove that that's true, so now we need to finish off with our conclusion. Remember the conclusion, you just go through all the steps. So, the statement is true for n equals 1, and assuming it's true for n equals k, it's also true for n equals k plus 1. We just saw that there. So by induction, the statement is true for all, and then take that bit just from the question, for all positive integers n. Woo! Well done. Example 9, prove by induction that n cubed take away n is always divisible by 6 for all n belonging to n. This upside down A, or the V with a line across it, means for all. So that's for all n, which is the number that you've got. And then that's going to belong to, that's what the E means, belongs to n, your natural numbers. So, for any of these questions, when it's proof by induction, I always write down SACC. So I've got a starting value. So the starting value, let n equal 1. So if n was equal to 1, we'll just sub that in here. This example is slightly different because we don't have a left-hand side and a right-hand side, but you still want to follow these steps and go through it the same way. So if n was equal to 1, then n cubed take away n would equal 1 cubed take away 1. And if you work that out, well, 1 cubed is 1, take away 1, and you get 0. If you end up getting 0, well, yeah, 0 is divisible by 6. 0 divided by 6 is 0. But you may wish to try another number as well. So after n equals 1, you may wish to go on to try 2, just to check if it's working for that as well. So if n was equal to 2, well, instead of n cubed take away n, you would have 2 cubed take away 2. And if you work that out, that will give you 8 take away 2. Which gives you 6. And you can see then, well, we were asked to prove that it's divisible by 6. Well, yeah, we get 6 when n equals 2. 6 is divisible by 6. So you can say then it's true for the starting values of n equals 1 and n equals 2. So we've dealt with the starting values. After that, we want to assume that it's true. So we say assume true for n equals k. Assuming it's true for n equals k then, well, our n cubed take away n will be, well, if n is equal to k, you replace n with k. So that will be k cubed take away k. We're assuming that's true though. Well, what we're assuming is true? Well, we're assuming that it's divisible by 6. So if k cubed take away k was divisible by 6, then it means it would have to be 6 or 12 or 18 and so on. It would have to be something in the 6 times table. And if it's in the 6 times table, well, every number in the 6 times table is 6 times something. So we can say that is going to be equal to 6 times, and then replace the word something just with a letter. I've not used a yet, so I'm just going to use a. So you know k cubed take away k, if it's divisible by 6, it must be equal to 6 times something. For example, if it was 12 that you get, well, you know that's 6 times 2. If it was 18, you know that's 6 times 3. Everything in the 6 times table must be divisible by 6, so it's 6 times something. Because we're bringing in another letter, we're just going to say, okay, a is a natural number, and it is divisible by 6. After that, well, that again above the pink line is just what we had on the last page. We assume that it's true for n equals k. After we assume it's true, we then have to consider n equals k plus 1. So what we do after that then, n cubed take away n will become k plus 1 cubed take away k plus 1. So replacing the n with k plus 1. To work that out, what do? Well, just multiply out the brackets. So k plus 1 cubed, you could go to the side to work that out, or you could use your binomial theorem. Because you've got k, you know k is going to be the power of 3, then 2, then 1, then 0. The 1 is going to be the power of 0, then 1, then 2, then 3. And you're also going to have these binomial coefficients from Pascal's triangle. Remember, Pascal's triangle starts with 1, 1, 1, then you've got 1, 2, 1, and then 1, 3, 3, 1. So you're going to have the coefficient of 1 there, then 3, then 3, then 1. We've also got this take away k plus 1, so just get rid of the brackets. You're taking away k, and you're also taking away 1. From there, what you could do is you could gather all the like terms together, but if you think about it, for all these previous questions, what you want to do is you want to take this part that you're assuming true and somehow sub that in down here. Well, the bit we're assuming true in terms of k is the k cubed, take away k. And here we've got a k cubed and we've got a take away k. So I want to leave them just as they are. So if I take them just first of all, I've got a k cubed to take away k. So I'm just leaving those parts. I've got that k cubed, I've got that take away k. And what am I left with? Well, I've got a 3k squared, I've got a plus 3k, and I've got this plus 1 minus 1. So just cancel them out. Really with k cubed take away k, well what's k cubed take away k equal to? If you look back to the stage where we assumed it's true, we said that because that's divisible by 6, it's going to be 6 times something. And we said that was equal to 6a. So with k cubed take away k, we can replace that with 6a. We've still got this plus 3k squared, and we've still got this plus 3k. Really, with the 3k squared and the 3k, you could take out 3k as a common factor. So that would be 3k bracket k plus 1. Where do we go from there? Well, we're somehow wanting to prove that this is divisible by 6. And the way we do that, well, the 6a, we know that's divisible by 6 because it's 6 times something. But it's this part that we have to look at. Really what we've got so far is we've got a 3, but we're really wanting 6 times something. However, if you think about it, you've got a k and a k plus 1. So k can be any number at all, pick any natural number, and k plus 1 will then be 1 above it. So really what you've got is 2 consecutive numbers. And if you have 2 consecutive numbers, in other words a number and the number straight after it, one of them will always be even. So pick any 2 numbers, so if you pick 9 and 10, well you've got an even number there. If you pick 10 and 11, again you've got an even number. 17 and 18, you've always got an even number. And if you have an even number, well the even number will be divisible by 2. Which means if you multiply the k and the k plus 1 together, you will always get 2 times something. You'll get something that you can rewrite as 2 times something, because one of these numbers, either the k or the k plus 1, will be divisible by 2, so it's going to be 2 times something. So what we can say then is the 6a will just stay as it is, but we'll have 3 times, and because one of these numbers will be even, it will be divisible by 2, so we know then that we can write the k times the k plus 1 as 2 times something. Again, I'm bringing in another letter and just saying it's going to be equal to b, and b is a natural number. After that, well, you've got a 3 times 2, you know that's 6, so really we've got 6b. Take out the 6 as a common factor, so that's going to be 6 times the a plus b, and really what that means is you've got 6 times something. A plus b is going to be a natural number, so let's just bring in another letter again, let's just say that's c. So just tidy it up completely. Again, c will be your natural number. So what that means is you're considering n equals k plus 1, and we now have down to 6 times something. And if we're getting down to 6 times something, then we know it is going to be divisible by 6. So this implies that n cubed take away n is divisible by 6 for n equals k plus 1. Once again, above the pink line is what you had just on the last page. We have considered n equals k plus 1. We've proved that it's divisible by 6, so now we just have to conclude that. And again, you just want to go through your steps. For every single one of these proof by induction questions, the conclusion is pretty much identical. It's just this very last part that will change. So we are saying here the statement is true for the starting values of n equals 1, and we also tried n equals 2 as well for this one. And assuming it's true for n equals k, it's also true for n equals k plus 1. So by induction, the statement is true for all n belongs to n. And that is your answer. Yeah. Last example, example 10, prove by induction that 3 to the power of 2n, take away 1, is always divisible by 8 for all n belonging to n. So in other words, for all n, there's going to be a natural number. Proof by induction question. So I always write down SACC, start, assume, consider, conclude. So we're wanting to have a starting value. Starting value, let n equal 1. So if n was equal to 1, well, the 3 to the power of 2n, take away 1, would equal, replace n with 1, it'd be 3 to the power of 2 times 1, take away 1. If you work that out, well, that's 3 to the power of 2, which is going to be 9. You're taking away 1, which is 8. Woo! We get 8. We get a number that is divisible by 8. 8 divides by 8. So we know then that is true for n equals 1. Make sure that you write that. What do we do after that? Well, we had our starting value, so now you want to assume it's true for n equals k. So assume true for n equals k, write that down. If it was true for n equals k, you would say then that 3 to the power of 2n take away 1 would equal, and you have replaced n with k, so that would be 3 to the power of 2k take away 1. And if that was true, then that there would be divisible by 8. And if that's divisible by 8, you know you could rewrite that as 8 times something. So you can say then that 3 to the power of 2k take away 1 is going to be equal to 8 times, and then whatever the something is, we'll just call that a. A belongs to n, and a is going to be a natural number, and is equal to 8a since it's divisible by 8. Every number in the 8 times table is divisible by 8, so you can say it's going to be 8 times something. So we have assumed that is true. Where do we go next? Well, we want to consider. What do you consider? Good, you consider n equals k plus 1. So now you're taking the 3 to the power of 2n take away 1, and you're considering n equals k plus 1. So replace n with k plus 1. So we've got 3 to the power of 2 times k plus 1, and we'll still get this take away 1. Where do we go from there? Well, let's just multiply out the brackets. So that's 3 to the power of 2k plus 2, take away 1. And now you want to think about your index rules. Remember, if you had 3 to the power of 2k times 3 to the power of 2, well, you could put them together and add the indices. What you want to do here is you want to go back the way. So you want to split that back up and say that's the same as 3 to the power of 2k times 3 to the power of 2. Remember, what you've done an awful lot of the time is gone back the way there. So if it's the same base, you've added the indices. Split it up. If you're adding the indices, split it up so you've got 3 to the power of something times 3 to the power of something. So we've got 3 to the power of 2k times 3 to the power of 2. And we've still got this take away 1. Where would you go from there, Olivia? Good. Well, you know 3 squared is 9, so let's just write that as 9. Why not? Where do we go after that? Well, this is the step that we're wanting to somehow take apart from here and then sub it in here somewhere. And really what we've got here is 3 to the power of 2k take away 1. So we're wanting to somehow get down to 3 to the power of 2k take away 1. However, this 3 to the power of 2k is locked in with this times by 9. We're not just going to take 3 to the power of 2k and then this take away 1 on the end. We're wanting the 3 to the power of 2k and then a take away 1 beside it. But we're multiplying it by 9. But you know what? Let's just force it in anyway. So let's replace that 3 to the power of 2k with 3 to the power of 2k take away 1. So if you replace that in there, well, what will that give you? Well, if you rewrite 3 to the power of 2k as 3 to the power of 2k take away 1, we're still multiplying it by 9. So around the brackets, we've still got this 9. However, if you multiplied it out, well, this line here, you'd have got 9 times 3 to the power of 2k. And here you've got 9 times 3 to the power of 2k. It's what you want. But you've also got this 9 times negative 1, which is negative 9. So we're taking away 9. We don't want to have this take away 9. We don't have it on the line above. So what we need to do is correct for that take away 9 by taking at the very end and add 9. So we've still got that take away 1 there, and at the end, to correct for that take away 9, we add 9 just on the end. Where do we go from there? Well, next, what you could do, if you've got this take away 1 and plus 9, don't write take away 1 plus 9. You know that's just going to be plus 8. So we can rewrite that as plus 8, and then after that, well, the whole point in doing that is we've got this 3 to the power of 2k take away 1, but we know from this line that we assumed to be true, well, if it was true, we know then that 3 to the power of 2k take away 1 is equal to 8a. So what we do is we replace this part here with 8a. So instead of 3 to the power of 2k take away 1 times 9, we've got 8a times 9, and we've still got this plus 8. What we can do there is you could always just multiply with the brackets there and then take out a common factor of 8, or you could just do that straight away. So taking out a common factor of 8, it becomes 8 times, and then we're multiplying 8 by the 9a, and then it'll be 8 times 1 there to get to 8. So I'm just taking that out as a common factor. But really, if you think about it, the question asked us to prove that it's always divisible by 8. And if you look at this, we've got 8 times something. So in other words, well, you can replace the something just with b. So this 9a plus 1 you can write as b, so it's going to be 8 times b. Again, you're bringing in another letter, so you're saying b belongs to n. Because you've got 8 times something, then it is always divisible by 8. So if you do 8 times something, you're just going to get all the results in the 8 times table. Every result in the 8 times table will be divisible by 8. So this implies that 3 to the power of 2n take away 1 is divisible by 8 for n equals k plus 1. What do you have to do after that? Good, you just finish that off with your conclusion. So once you get down to that line, again, everything above the pink line was on the last page. All we're doing now is just finishing that off. And you finish it off by just going through all of these steps to start, assume, consider. So the statement is true for a starting value of n equals 1, you prove that. And assuming it's true for n equals k, it's also true for n equals k plus 1. This is proof by induction, so say by induction, the statement is true for all n belonging to n, and that is your answer. That is it for proof by induction. It's only 2 lessons long. There are 10 examples there in total. Woo! Enjoy working through them. Best of luck. Look back to any of these examples if you are unsure. Just make sure though that you set them out the exact same way that I'm doing it. And if you wish to use the start, assume, consider, conclude, if you wish to use SACC, feel free. Have fun. Bye. Yeah.